Welcome back. Today we're going to look at how to use the electrochemical series in electrolysis. So we find the electrochemical series in the data book. It's item 2 on page 3. So you can see on the right the electrochemical series. The strongest oxidizing agent of the whole table is fluorine gas. And as we go up the left-hand side of the table, we have increasing oxidizing strength. So all the way from lithium ion to fluorine, fluorine is the strongest oxidizing agent. The strongest reducing agent we find on the right-hand side of the double arrows. So lithium solid is the strongest reducing agent, and from fluoride ion to lithium solid, we have increasing reducing strength. Now, whether you're talking about galvanic cells, fuel cells, or electrolysis, the strongest oxidizing agent is always reduced, and the strongest reducing agent is always oxidized. An important thing to remember in electrolysis, if you've got an aqueous solution, don't forget water. So if we have a solution of potassium iodide, our species are K plus aqueous, I minus aqueous, the iodide ion, and water. We must not forget water. So here I've got the electrochemical series divided into 2 so that you can read it a bit easier, but I locate my species. I had potassium ion, I have iodide ion, and I have water appearing a number of times. Now, if you have a look at 1.51 E0 volts, there's manganese 2 plus and water. Don't worry about the water there because I don't have any manganese 2 plus. Once I've located the species that I've got, I want to identify the strongest oxidizing agent, which is between water here and potassium ions. The water is further up on the left-hand side, so it's a stronger oxidizing agent. And then I look for the strongest reducing agent, and the iodide ions are lower down on the right-hand side, so the iodide ions are the strongest reducing agent. If I combine the 2 sections of the electrochemical series so that you can see it as a whole, then you can see the strongest oxidizing agent is water at minus 0.83 volts, and strongest reducing agent is iodide at positive 0.54 volts. Between those 2, the strongest oxidizing agent and the strongest reducing agent, I have a positive gradient. A positive gradient means it's an endothermic reaction that requires energy input. Always, the strongest oxidizing agent is reduced, so the bottom reaction goes forward. The strongest reducing agent is oxidized, so the iodide ions go backwards. Then I can write the half equations based on the selection there. Now, the half equations both have 2 electrons in them. If you have a different number of electrons, you multiply the half equations so that you have the same number of electrons. It's always useful to think about what would be happening if you were observing this reaction. Producing hydrogen gas means you'd have bubbles appearing, and producing hydroxide ions means that you would have a high pH. So you could detect that with phenolphthalein indicator, for example. Write down the observed state. Now, from the electrochemical series, it says that iodine is a solid, but if we electrolyze this in solution, we would see that it actually starts to drip away. So it's either aqueous or liquid. So we'll put aqueous for our half equation. To write the overall redox equation, we add the 2 half equations together. We cancel out the electrons, and then we're left with our balanced redox reaction. So 2 waters, liquid, plus 2 iodide ions, aqueous, react to form hydrogen gas plus 2 hydroxide ions, aqueous, plus aqueous iodine. To calculate the minimum cell voltage, there's two ways that we can do this. We can either just take the top E naught minus the bottom E naught, or we can say the E naught of the reduction half equation minus the E naught of the oxidation half equation. This is the formula that's given in the data book. So I locate the two E naught values that you can see in green. The E naught of the cell, if I take the reduction half equation, it's negative 0.83 volts minus positive 54 volts is 1.37 volts. Now, voltage can't be a negative thing. So if you have a negative, just remove the sign and make it positive. Importantly, you can see here I've got a greater than or more than sign. I actually need to put in more than the minimum voltage at standard lab conditions, which is 1.37 volts. I need more than that for overpotential to drive the reaction. Good luck. You can do this and see the links to the website in the comments section. See you soon. Bye.